welcome to this explainer. Today, we're going to track the absolute obstacle course that a tiny piece of silicon goes through to become the technology that literally powers our modern world. Now, before it even reaches the back-end facility, a semiconductor wafer has already survived anywhere from 500 to 1,200 incredibly complex microscopic steps in the front-end fab. But what happens after all that? How do we actually transform a fragile exposed silicon die into a fully functional, ready-to-use black-boxed integrated circuit? Well, let's dive right in and trace that exact journey together. Here is our roadmap for today. First, we'll look at the big picture of the back-end journey. Second, we'll dive into wafer sort and probing. Third, cutting and attaching. Fourth, wiring and encapsulation. And finally, number 5, the final quality test. All right. Let's kick things off with Section 1, the back-end journey, going straight from wafer to integrated circuit. So, taking a macro view here, raw wafers don't just magically become those little black chips you see soldered onto a motherboard. They have to pass through 3 major checkpoints. Step 1 is probing and sorting, basically figuring out which chips actually work. Step 2 is physical packaging, where we protect and connect them. And Step 3 is a final quality test to guarantee absolute perfection. Let's zoom in on that very first checkpoint. Moving on to Section 2, wafer sort and probing, our very first major checkpoint. The crucial step here is called chip probing, or sometimes you'll hear it called wafer sort. I want you to imagine a highly advanced microscopic lie detector test. A specialized tool called a probe card comes down right onto the uncut wafer, touching 2, 4, 8, or even 16 dies all at the exact same time. It's running hundreds, sometimes thousands of rigorous electrical tests. It's checking voltage, frequency, critical currents, overall efficiency, you name it. And it's evaluating every single die before a saw ever touches the silicon. And the results of that intense probing give us a highly detailed digital map. The flawless dies, the ones that pass every single test, are categorized as bin 1. These are usually color-coded green, and they are our winners. On the flip side, the ones that fail get a specific fail bin code, and historically, they're marked with a literal physical dot of ink. Why go through all this trouble? Because we have to separate the good from the bad right away. There is absolutely no way we want to waste wildly expensive packaging materials and machine time on a chip that's already dead on arrival. That brings us to Section 3, cutting and attaching, where we finally physically separate those winners. First things first, to keep power consumption low and ensure these chips can actually fit inside tiny, modern devices like your smartphone, the back of the wafer is physically ground down until it's literally paper thin. Because it's now incredibly fragile, it gets secured onto this specialized blue tape. And this tape is honestly genius. It holds everything perfectly in place so that when the diamond saw comes in and slices the wafer up, the tiny chips don't just scatter everywhere across the factory floor. Next is the die attach step. And remember that lie detector test we just talked about? Well, here's where it totally pays off. The assembly machines completely ignore any of those ink-marked bad dies. They zero in on only the perfect green binned chips, carefully plucking them right off the blue tape. Then they physically glue them to a metal skeleton, which we call a lead frame, using a highly conductive silver paste. Now for Section 4, wiring and encapsulation. This is where we build the iconic black box. The sheer precision in this next step is honestly mind-blowing. High-purity gold or copper wires are physically stitched between the microscopic silicon die and the metal pins of the lead frame. We call this wire bonding. But those wires are incredibly fragile, so immediately after, to stop them from breaking or oxidizing in the air, the whole assembly gets encased in a hardened plastic mold. It's baked into that recognizable black box shape you're probably familiar with. Finally, a laser or printer steps in to brand the outside with the customer's specific logo and device ID. But hold on, we aren't totally done yet. Once the chip is sealed up and branded, it goes through a mechanical process called trim and form. Any excess metal from that initial skeleton frame gets trimmed away, and the remaining metal pins are carefully bent downward. This officially gives the integrated circuit its recognizable, pluggable little legs, making it completely ready to be mounted onto a circuit board. Which brings us to our last step, Section 5, the final quality test, the ultimate guarantee. Enter the final test, or FT for short. This is the gauntlet. We are ensuring 100% operational perfection here. That means validating speed, power consumption, and reliability all over again from scratch. They'll even place these newly packaged chips into literal ovens, running performance tests in extreme high and low temperature environments just to guarantee they're going to survive out there in the real world. Now, you might be asking yourself a very logical question right about now. If we just spent all that time, money, and effort testing every single chip at the very beginning during chip probing, why on earth we need to waste time testing the exact same chip all over again at the end? Doesn't that just seem super redundant? Well, it actually comes down to a really critical business strategy. If we look at the different goals here, we see that these two tests serve entirely different purposes. The wafer sort at the beginning, that saves the manufacturer money by filtering out dead chips before they waste expensive packaging on them. But the final test, that protects the customer. It ensures that all the intense physical stress of grinding, sawing, gluing, wiring, and molding didn't accidentally damage the chip during assembly. But there is one really fascinating exception to this rule. What if a specific manufacturing process is so incredibly mature, so perfectly dialed in, that it actually reaches a yield of 99.999%? In these super rare, highly stable scenarios, factories can make the strategic call to just skip the initial chip probing entirely. Think about it. If you know basically every die is a winner, it's actually cheaper to just package the tiny handful of bad ones and patch them at the final test, which dramatically speeds up your entire production timeline. So, to wrap up this explainer, the journey of a die is basically a carefully orchestrated balancing act. It is a continuous trade-off between catching flaws early to save manufacturing costs, precisely encasing incredibly fragile technology, and ultimately guaranteeing pristine, absolute perfection at the finish line for the end user. And that leaves us with a pretty fascinating thought to chew on regarding the future of all this. As our smart factories get even smarter and front-end yields inch closer and closer to an absolute 100% perfection rate, what happens to this rigorous obstacle course? When every single die is a guaranteed winner right out of the gate, which of today's mandatory checkpoints are just going to completely vanish tomorrow? Thank you so much for joining me on this explainer, and keep questioning the process.